So in this chapter, I'm going to introduce the concept of Lewis dot diagrams. But in order to do that, we need to review valence electrons. So remember, the periodic table is very helpful because it shows us how many valence electrons elements have. So if you're in group 1, your alkali metals and hydrogen, you have 1 valence electron. If you're with your alkaline earth metals, you have 2. Then we're going to skip over the transition metals and to the group with boron. That would be 3, 4, 5, 6, 7, and 8 valence electrons. However, what happens if you have a trickier one? So for example, what if you have a transition metal? So let's look, for example, at zinc. Okay? I'm going to really quickly write out the shorthand electron configuration for zinc. So keep in mind, to write the shorthand electron configuration, you're going to move up a group, you're going to move up a row across to the noble gas, which would be argon, and you're going to put that in brackets, and then you're going to keep reading. So I go down to where potassium is, that would be 4s2, and then 3d10. So looking at this and remembering that valence electrons are the electrons in the outermost energy level, this tells me that zinc, because 4 is the highest energy level there, has 2 valence electrons. So those are the trickier ones. It's still not that tricky, it's just that you can't count using the periodic table. So zinc has 2 valence electrons. So you're going to complete the rest of the problems that I gave you, and then we're going to move on. So you're going to learn in this video how to create Lewis dot diagrams. So there are specific steps that you need to take to make sure that you're doing it correctly. And the steps are CSLC. So let's look at each of these. So C stands for count the number of valence electrons. So we'll look at that in just one second. Next, you're going to share electrons between elements. Then you're going to add lone pairs to the outer elements and then to the central element, and we'll look at that. And then you're going to count the number of electrons used, and that needs to match with the number of valence electrons. If it doesn't, then we have to problem solve, and so we'll get to that in class.
So I'm going to show you how to draw the Lewis dot diagram for water and for phosphorus tribromide. And I'm first going to show you how to draw it without the model kit. Then I'll show you with the actual physical model kits that you guys will have in class. And then using that, I will then draw it properly. Okay? So if I look at this, I have water, so I have H2O. So remember, my first step is that I need to count my number of valence electrons. So hydrogen each have 1, so I'm going to do 1 times 2. And oxygen has 6, so that's a total of 8 valence electrons. My next step is to have those atoms share electrons. So oxygen's going to be at the center because I only have 1 of them. And I'm going to have it share electrons with hydrogen. My next step is to add lone electrons. So remember, every atom on the periodic table, except for hydrogen and helium, want 8 valence electrons. Okay? So hydrogen right now, because I have this bond right here, this bond represents 2 electrons. So hydrogen sharing 2 with oxygen. So each hydrogen right now has 2 already, so it's happy. So it's not going to want more electrons. So I'm not going to put any lone electrons on this guy. But oxygen right now only has 4 electrons total. So I need to add 4 more. So I'm going to add 2 more pairs. So 1 pair there and 1 pair there. Okay, so now oxygen has 8 electrons. Now I need to count again because remember, I need to use 8 valence electrons. So right now I'm using 2, 4, 6, 8 electrons, which is how many electrons I should be using. So this is a perfectly fine Lewis diagram, but now let's look at it using the model kit.
So if I'm going to create my first molecule, okay, if I'm going to create water, here's my oxygen atom. Now notice it has 4 holes in it, so there are 4 possible different slots for it. So I'm going to put 1 hydrogen here, and it doesn't matter where you put the other hydrogen at all. You can put it in whichever slot you want to be able to put it in, okay? So this is the correct model for water. Notice I've got those 2 holes on top which represent the lone pairs of electrons. So looking at this, I'm now going to draw it properly on paper.
So using the model kit, as you noticed, Your oxygen's going to be here, but because of your VSEPR model, which states that atoms are going to be located in such a position to minimize the repulsive forces of electrons, okay, my oxygen's going to be here, my hydrogens are going to be like this. Or you could totally flip it and have it up above, but I tend to draw it like this. And then the lone pairs of electrons, which on that model kit are represented with those empty holes, your lone electrons are going to be up here. Okay, so while this is correct in the sense that I have the correct number of electrons, this is the correct structure, and this is how you would need to draw it on a quiz or test. So you will always have your model kit available so that you can draw it properly. At a certain point, you're going to get so used to doing this that you're not going to need your model kit. But just as a quick review of the VSEPR model, why this is correct but this one isn't. Remember, your electrons are going to repel the atoms, so they're going to force them downwards. And so in order to minimize that repulsive force of the electrons pushing down on that hydrogen atom, your hydrogen atoms are going to be here versus here because they're going to be pushed downwards. Okay, so let's look at another example. We've got PBr3. So for PBr3, I've got to first count my total number of electrons. So for phosphorus, I have 5 valence electrons. For bromine, I have 7, so it's going to be 7 times 3, so I'm going to have a total of 26 valence electrons. So if I draw this without thinking about my VSEPR model, I'm just going to share electrons. So I have 1, 2, 3 bromines coming off of this. Remember, every atom, except for your hydrogen and helium, need 8 valence electrons. So right now, this bromine only has 2, so I'm going to add 6. I'm going to add 6. And I'm going to add 6. Then, phosphorus right now has 2, 4, 6, so it needs 2 more. Okay, now let's look at it using the model kit. For PBr3, I'm going to take my phosphorus. I'm going to take this black ball again. Okay, remember you've got 4 different possible places to place your atoms. Okay, I'm going to put 1 here. Okay, so 1 bromine there, 1 bromine there, and then finally 1 bromine there. Okay, so if you look at this, notice you've got 1 lone pair of electrons here, which we're going to represent in a second, but the way we're going to draw this is with it moving downwards, downwards, and downwards to try and show that 3D shape. Because notice it isn't flat. If you drew 1 up, 1 down, that would imply that this was flat, but notice it's not. So we're going to go downwards, downwards, downwards for drawing. So let me show you that. So based on the model kit, phosphorus is going to be in the center. It's going to have 3 bromines, and they're going to be forced downwards like this, because you then have your lone pair of electrons on top. Now, I'm going to stop drawing the 2 dots simply because it takes more work. Instead of drawing the 2 dots, you can simply draw 1 line, and that represents 2 electrons. Okay? Then I need to add my 6 electrons, so I'm going to add 2, 4, 6, 2, 4, 6, 2, 4, 6, and that is the proper structure for PBr3, the Lewis dot structure, taking into consideration your VSEPR model.